My name is Pejcha. I'm a graduate student at The Ohio State University, and I'm here to report on a recent paper which is entitled Varying a Binary, Dynamical Mass Loss and an Optically-Thick Wind Explain the Candidate Stellar Merger V1309 Scorpii. I'd like to introduce you to some of the basic points that I make in the paper. V1309 Scorpii developed an unusually red color during its 2008 outburst and joined a group of enigmatic objects such as V838 Mon. One possible explanation of these objects is that they are mergers of main sequence stars. V1309 Scorpii solidifies this view because the pre-outburst photometry revealed a binary star system with a rapidly decaying orbital period. In this paper, I focus on two important but neglected features of V1309 Scorpii: the rapidly accelerating orbital period decay and the slow 200-day rise to optical maximum. This figure shows the orbital period evolution of V1309 Scorpii prior to its outburst as measured by Telenda et al. 2011. The period decreases accelerating with time. The decay timescale decreased from about 1000 years to about 170 years in less than 6 years. A change by a factor of about 6 over a timescale that is at least order of magnitude shorter than the period decay timescale is very surprising. Since the period decrease eventually ended in an outburst and potentially a merger, it is imperative to understand the mechanism of the period change. It was suggested that the period decay is caused by the Darwin instability. The orbital evolution equations suggest that for any tidal process, first and second period derivatives change on the tidal friction timescale. Since the final first and second period derivatives are much shorter than tidal friction timescale, the period decrease of V1309 Scorpii cannot be explained by any tidal process. Dynamical friction decreases the orbital period when the binary orbits in a non-rotating envelope. This cannot be responsible for the period changes in V1309 Scorpii, because the required common envelope density implies that the optical depth through the medium surrounding the binary would have been hundreds to tens of millions. Yet, we observe the binary. The accelerating period decrease of V1309 Scorpii must be due to the onset of an instability that operates on a timescale much shorter than tidal friction timescale, yet longer than the dynamical timescale. This is compatible with dynamically unstable mass loss, which occurs when a star tends to adiabatically expand as a response to a removal of surface layers. The non-conservative part of the dynamical mass loss forms a wind. As the dynamical mass loss runs away, the mass loss rate increases and the wind eventually forms a photosphere. The binary optical radiation will be replaced by that from the photosphere of the wind. The binary becomes obscured. From this point, we observe the luminosity of the optically-thick wind, which is dictated by the physics of the dynamical mass loss. This explains the slow rise to optical maximum, as shown in the figure. By combining the directly observed orbital period change and the slow brightening due to the optically-thick wind, it is possible to constrain the total mass loss evolution of the primary star in V1309 Scorpii, as is shown in this figure. This plot summarizes and generalizes the estimates of physical processes in V1309 Scorpii to a range of orbital periods. For binaries with periods smaller than about 1000 days, the common envelope becomes optically thick before dynamical friction can cause a decay of the orbit. Physical conditions in longer period binaries can allow for dust formation, and the associated high opacities would cause binary obscuration for much lower mass loss rates than in V1309 Scorpii. Therefore, it seems unlikely that binaries undergoing dynamical friction will ever be directly observed. If common envelopes are produced by dynamical mass loss, the density of the common envelope evolves along a nearly vertical line as shown for V1309 Scorpii. This figure implies that most binaries will produce an optically thick wind before other effects become important. For radiatively inefficient winds, the wind luminosity will be negligible compared to the radiative luminosity of the binary for periods larger than about 10 days. Nonetheless, the total optical depth to the binary can still be large, especially if dust forms, which will make the luminosity of the object essentially the same as in its unobscured state, but the observed effective temperature will be much lower. If the dynamical mass loss lasts a short amount of time, the results would be an expanding cold dusty shell. Such obscured objects could potentially be identified by infrared observations. This new class of transients driven by dynamical mass loss deserves much more detailed and realistic calculation. If you'd like to read more about the details of the results and methods, please take a look at my paper which was posted on the astro-ph archive today.